Hi, we went through the basics of limits in the previous video, and so we'll continue with other forms of limits in this video and build a better understanding on limits. Let's begin. In the previous video, we have already shown and we have used the precise definition of limits to prove when a limit exists. And so, now the question is, when does a limit not exist? And so a limit does not exist, we need to prove the negation of the statement. So the negation of the statement that L is not the limit is there exists a epsilon such that for all delta, the following does not occur. And if we want to prove that the limit does not exist, we need to prove it for a general L. An example would be this piecewise function that there is a break in it. If we take our epsilon to be half, then for any delta larger than 0, we can always find an x from 1 plus delta within this interval. And so, no delta satisfies that inequality, and hence the limit is not half. And so we can do this for any L, then we can say that the limit does not exist. And so if we prove the negation of the statement for a particular L, it only proves that the limit is not L, but it does not prove that the limit does not exist. And to prove that, you just need to use a general L. Also, there is this concept of one-sided limits. This can also help us prove when limits do not exist. We'll start by understanding what are limits, one-sided limits, and actually, it is how you want the intuition to be. We are just taking the limit from coming from one side of the interval. And so we can say that the left-hand limit, when the limit comes from the left, meaning the intervals are all on the left, and it approaches from this left side, is one value, and the limit from the right is where all the intervals are from the right. And you can see the definition written out intuitively over here. So we say that fx becomes arbitrarily close to L as x approaches C within the interval from C to B. So that means C to B is around, C is this value, let's say, and B is somewhere here, and so the interval gets closer and closer from the right. And similarly for the one on the left. And we denote it by C plus for the right and C minus because everything is less than C. And then the intervals are bigger than C for the right hand side. It can approach different limits, as you can see from this function, x over modulus x. And so, the limit from the right is 1, while the limit from the left is minus 1. And precisely, we will say that it means that for any epsilon, there exists a delta such that x minus a is less than epsilon. X minus a now is not, now in the previous, and you have the definition of a limit, it is modulus x minus a. But now you only care that x is greater than a and less than a plus delta because it is only the right hand side of the interval. It will imply that the following is true. So this just means x is sufficiently close to a from the right and fx is arbitrarily close to L. And you can make the similar definition for the left hand limit. But in this case, you want x to be within a minus delta to a, which just implies that it is a minus x less than delta. And with this precise definition, it allows us to prove functions that only have one-sided limits at certain points. For example, the square root of x minus 2. You cannot find any x value less than 2, or else this function is not defined. And so you can only take the right hand limit, and that is the point of defining right hand limits. You can see the proof of why the right hand limit is 0, and I'll let you read it up on your own. We'll be moving on to understand more about limits. Now, understanding the one-sided limits, the other type of limit is the infinite limit. And the infinite limit says the following: if we take x sufficiently close to a, the value of fx becomes super large. For example, the graph of y equals to x squared. Or better yet, the graph of 1 over x. As x approaches 0 from the right, fx becomes super large. And so what does this mean? It means that for any positive value, there will exist an interval such that fx is always greater than this positive value. So you can just keep increasing this positive value to a very large value, to any large value actually, and you can always find x that satisfy the following near a. And this means that the limit near a of fx as x approaches a is infinity. And similarly, if m is less than 0, then we say the limit is negative infinity. But because infinity is unreal, we still say that the limit does not exist. And so this gives us a way to show that the limit does not exist by proving that the limit is either infinite or negatively infinite. For example, we have the function 1 over x squared. The graph looks like this. Now we know that as x approaches 0, the limit will become infinite. And so we just prove it by definition. For any number m, we need to find a delta such that this holds. However, we know that 1 over x squared modulus larger than m. We can take out the x squared because it's already positive, and we just need to show that the following occurs to prove this occurs. And so we can see this shape is of the form over here. And so we just take the delta to be 1 over m squared. You reciprocate it will be larger than m, and then you square it will become m. And hence, the limit of this function 1 over x squared is infinity. We can see from this example how we use the precise definition to prove that the limit is infinity. We can also have one-sided limits for functions that go to infinity. For example, the 1 over x, the limit from the right is infinity, while the limit from the left is minus infinity. And so everything just boils down this definition, and you can just play around to get what you can play around your intuition to understand what should be the definition for the limit. Lastly, for the topic of limits, we want to prove this very important theorem to help us prove limits of functions that are very hard to directly use the precise definition. So in this case, if you were to read the textbook, you'll see that they will prove that the limit as x approaches 0 of sine x over x equals to 1. But in order to do so, they will actually bound sine x over x to be in between 1 and cosine x. And so as x approaches 0, this side stays as 1 and cosine x stays as 1. And so now the idea is just squeeze between two sides that approach 1. And so you want your value of this limit to also be 1. And what does this mean? Is that if you are able to find an interval such that fx is less than gx, which is less than hx, and the value as x approaches a is L, and hx as x approaches a is L, also L, then the limit of this function squeezed in between has to be L. And we can prove this using the precise definition. So we want to let epsilon be any value, and we want to find a delta such that the following occurs. Since we know that the limit of fx is L, we can take this epsilon and we can find a delta 1 such that x minus a within delta 1 implies that fx minus L is less than epsilon. This means that minus epsilon is less than fx minus L less than epsilon. And similarly, we can do the same for hx. And we can find a delta 2 such as the following occurs. And because you know that this inequality occurs within some interval, there exists an interval such that the following occurs. And then you can minus L on all the sides, and you get the following. And so, this means that if you can take the interval small enough such that this inequality occurs, this inequality occurs, and this inequality occurs, so we take the minimum, it means that fx minus L less than gx minus L, which is less than hx minus L, because delta is less than or equals to R. But we also know that delta is less than or equals to delta 1, and so fx minus L will be greater than epsilon. And we also know delta is less than or equals to delta 2, which allows this right hand side to inequality to occur. And we see that gx minus L is now sandwiched, is less than epsilon and greater than minus epsilon. And so gx minus L, the modulus, is less than epsilon. This proves that the limit of gx as x approaches a is L. And hence, you're done with the proof of Squeeze Theorem. Online, you can also read it to be known as Sandwich Theorem, but they're all the same properties. And so, this helps us prove that the limit is L. We can also take a note that if we were to approach the limit from the left hand side and approach the limit from the right hand side and they do not equal, then the function the limit does not exist for that function. So, for example, in this case, the limit on the left is minus 1 and the limit on the right is 1. And so, we can say that the limit does not exist because they do not converge to the same value. And so the limit exists if and only if the left hand side and the right hand side limits exist and are equal to each other. There's some things to take note, and you can prove that as an exercise. You can see how that's the case by already seeing the Squeeze Theorem being used, but the proof does not require the Squeeze Theorem. Because if you define a function that only has this side and define a function from this side, this function in between, the combination of these two functions violates the Squeeze Theorem, because here equals to one limit and here equals to one limit. But it does not prove that the limit does not exist, it just proves that the limit does not equal to what you want. But you can actually prove it using the precise definition, and I'll leave it to you as an exercise. And so now that we have went through more ideas about limits and we have practiced more, we have shown what is a one-sided limit and we have shown what is infinite limit. We have also shown instances where limits do not exist. We'll be moving on to using these ideas of limits to build up our conceptual understanding of how functions behave. And that will be left to the next few videos. So I'll see you again. Thank you.